Name is Misha Aruj Khan, and today I am going to present our paper titled as GAANet Ghost Auto Anchor Network for Detecting Varying Size Drones in Dark. Among other authors are Maham Misbah, Zishan Kaleem, Yansha Deng, and Abbas Jamalipour. The contents of my presentation are as follows: Introduction, Literature Survey, Ghost Auto Anchor Network, Model Evaluation, Conclusion and Future Work, References. Introduction. Unmanned aerial vehicles are widely adopted in remote sensing advanced surveillance applications due to the growth in drone-based applications. According to industry insights, the global drone market is expected to reach 48 billion by 2026. Because of their flexibility and mobility, drones are widely considered in many daily and industrial applications, and their capabilities are further enhanced when equipped with advanced artificial intelligence techniques. This advancement and its increasing widespread use have raised serious concerns about the security of public places, as we have seen several instances where drones have caused damage to infrastructure. Therefore, effective detection systems are necessary for protection against malicious activities. And tracking systems are preferred over traditional object identification methods due to their less accurate target detection and high false alarm rate. Object identification is increasingly adopted for drone detection, but many schemes fail because of the drone's small size, high flight altitude, and fast speed. These issues are addressed by UAV detection systems integrated with deep learning algorithms. In literature, multiple techniques such as regions with convolutional neural networks (RCNN), faster RCNN, mask RCNN, YOLO, you only look once, SST, single shot multibox detector are used. Specifically, YOLO offers the finest all-around detection performance in speed, accuracy, and precision. Other techniques like radar, optical detection, and acoustic sensors are the most often used technologies for detecting UAVs. Ghost Auto Anchor Net. Proposed solution. In this paper, we perform multi-class and multi-target drone detection in challenging weather conditions based on infrared images utilizing an improved YOLOv5 P2 model. Contribution. Our main contributions are as follows. A customized dataset was created for multi-class IR images with varying weather conditions and multi-size targets. We improved the baseline YOLOv5 model by introducing an auto-anchor algorithm. The night vision IR images have very small or tiny objects. That's why we introduced an extra small anchor P2 in the model's head. We also upgraded the baseline standard convolution and C3 modules with Ghost convolution and Ghost. We also integrated AdamW optimizer, which improved the weight decay with respect to loss function. This figure shows the network topology of the proposed Ghost Auto Anchor network. We effectively use the Ghost convolution and C3 Ghost modules for performing optimized convolutions with the extraction of the most pertinent and unrepeated feature maps with no duplicate gradient, informing by maintaining accuracy with reduced complexity. The size of the input image is 256 x 256 because lower resolution images increase the generalizability of the GAANet and make it less prone to overfitting with a focus on important high-level features. The model's depth and the channel multipliers are set to 0.25 and 0.5 respectively. These values are chosen so that the model has the best functionality of Ghost modules in a lightweight package. The auto-anchor approach is used to apply a k-means function to the modified database labels. Then k-means centroids are used as the beginning conditions for a genetic evolution method. We used 1000 generations and investigated to get the final calculation of the proposed anchors with CIOU, complete intersection over union loss, and best potential recall as the fitness function. The proposed anchors receive fitness values of 81.08% on this dataset. The GhostNet box determines the locations of the bonding boxes X, Y, height, and width, scores, and object classes to produce an output image with a bounding box around the identified item and its confidence score. Model evaluation dataset. Here we propose GhostNet to successfully extract features from collected IR data in a low or no light conditions at night. To train the proposed GhostNet architecture, we gathered around 5105 IR images of birds, drones, planes, and helicopters from the publicly available open source datasets provided on RoboFlow. Model training. All experiments are separately run on the Google Colab environment with an NVIDIA Tesla T4 GPU having a low learning rate of 0.001, where GhostNet and GhostNet YOLOv5 has a batch size of 256 and 512. The epochs of both models are set for 500, but GhostNet YOLOv5 stopped training at 300 by using early stopping as the model performance stopped improving, while GhostNet stopped training at 457 epochs. Detailed comparison of the evaluation metrics. In this table, we can see the detailed evaluation of both trained models, GhostNet, which is proposed by us, and GhostNet YOLOv5. We performed comparison with respect to precision, recall, MAP. If we see the GhostNet model, it achieved the highest true positive value of 100 for drones and planes and lowest true positive of 72% for helicopters. GhostNet has the highest false negative rate for helicopters and planes at 12% and 46% respectively, while the GhostNet YOLOv5 achieved the highest true positive of 100 for planes and lowest true positive of 47% for helicopters. The stats prove that the improved and accurate detection ability of GhostNet for planes, drones, and birds, with only helicopters having a true positive less than 90%. The addition of ghost-based convolutions and C3 led to extraction of the most relevant feature maps with smaller channel sizes than the baseline model, resulting in a reduced model size, layers, parameters, and G-flops. The proposed GhostNet trained with 395 layers, and it took 3.210 hours to train on a completely customized dataset with a weight size of 14.1 MB. The layer size is reduced due to the smaller value of channel and depth of the GhostNet model compared to the baseline model. GhostNet has the highest object precision of 99% for helicopters and varied at varied sizes and altitudes, whereas planes have the best recall value of 98.3% and birds with the highest MAP of 98.6%. GhostNet has the lowest precision value of 90.4 for drones, which is 21.5% more than GhostNet YOLOv5, as it achieved 68.9% detection precision for drones. Similarly, the 18.4% higher recall is achieved for helicopters compared to GhostNet YOLOv5. Therefore, the overall precision of GhostNet is increased by 1.4%, recall by 2.3%, and MAP by 2.5% compared to the GhostNet YOLOv5. Now we can see the detection results achieved by the proposed GhostNet model. From top to bottom, you can see extra small, small, and medium and large objects present in the images. The first one is the bird, the second are the drone, the third is the helicopter, and fourth is the plane. For drone IR images, GhostNet achieved 94% accuracies for extra small images, while small, medium, and large IR drones images have 93% detection accuracy. GhostNet achieved 99% accuracy on small and large helicopter IR images. For plane detection, GhostNet attained 96% accuracy for extra small plane IR images. From these results, we can infer that GhostNet improved performance on all size target IR images, but it attained the best accuracy for extra small bird, drone, and plane IR images, which are quite difficult to detect. Now we can see the detection results achieved by the GhostNet YOLOv5 model. GhostNet YOLOv5 had the best testing accuracy for large bird IR images, of 89%, small drone IR images with 87% accuracy, medium helicopter IR images 89% accuracy, and large plane IR images of 76%. Comparison with the state of the art. The MFNet model performed UAV versus bird detection using visual images. Their proposed MFNet medium model achieved 95% recall with 95.9% MAP on drone images, while GhostNet has 98.3% recall with 97.4% MAP on drone IR images, which are 4.3% and 1.5% high respectively. The authors used GhostNet convolution in the YOLOv5 baseline model and achieved 19.89% less precision than GhostNet. YOLOv5 X all Ghost added GhostNet in both head and backbone and got 0.6% less MAP than GhostNet. GhostNet feature extraction network was embedded in YOLOv3 that achieved 8.3% less MAP than GhostNet model. Conclusion and future work. First, we will discuss the conclusion. As all of you can see in this presentation, we proposed an improved and optimized deep learning model for extra small size flying object detection, specifically UAVs using IR images during night surveillance. The proposed GhostNet used ghost convolution, ghost C3, and a downsampled input channel size to extract the most prominent and non-repeated features. Detailed experimentation was performed on a customized multi-class dataset containing drones, planes, helicopters, and birds. The results showed a low misclassification rate, which confirms the effectiveness of the proposed model for real-time night vision IR images. The proposed object detection approach outperformed the other current state-of-the-art technologies by a significant margin. Future work. In future, we aim to use multi-sensor integration in our model. We also aim to perform real-time tracking and identification of UAVs, and we aim to improve scalability and cost effectiveness of the proposed technique. References. These are the references that were used in this presentation. Thank you. If you have any queries and questions related to this presentation, please do contact us. Allah Hafiz.